Okay, so if you're watching this at home, we're going to go through a short little video on how to, on accuracy and precision and how to determine numbers of significant figures. So accuracy and precision and what the difference between those actually is. So there's a really easy way to explain it, and I think you talked about this in ninth grade physical science a little bit. Accuracy and precision. So if you are shooting an arrow at a target, your ultimate goal is to hit the bullseye of the target. And if you can do that, that means you're really accurate, usually. You're really accurate with your bow and arrow, right? So that's the ultimate goal. We want to hit the bullseye. So if you can do that, you're very accurate. If in chemistry, I might say if I give you a 1 gram sample and I know that's how much I gave you, and you find the mass of it on your electronic balance and you come up with exactly 1 gram, you are very accurate, okay? You have a high degree of accuracy. Precision is a little different. Precision means how close you are consistently. So if you shoot arrows at your target, so you're shooting your little bow and arrows at a target, you shoot 3 of them, 1 lands here, 1 lands here, 1 lands here. None of them have hit the bullseye, so that's unfortunate. It means you're not very accurate. And for those of you who deer hunt, maybe we're talking about when you sight in your deer rifle. What does that mean when you consistently, if you're sighting in your deer rifle and you consistently hit the same spot on the target, but it's really not what you were aiming for? What might be wrong? Your sight might be off. Maybe you have a tendency to always pull to the right, like some people out, like there's a variety of reasons, but you have a high degree of precision because you're consistent every single time. However, you're not very accurate. The ultimate goal was to hit the bullseye at the target. So precision is how close a series of measurements are to one another. So yes, if you measure the same sample multiple times, if I give you 1 gram of a sample and you measure it multiple times, are you getting 1 gram every single time? Or did you measure it one time and you got 1 gram and the next time you got 1.2, right? If you are getting those kinds of answers, then you're not very precise because you're not getting that same measurement over and over again. And if it's not even close, if I give you 1 gram and you get 1.2, and the next time you measure that same sample you get 1.4, and the next time you get 1.5 or 7 or whatever, then I would say you are neither accurate, you did not weigh it to be 1 gram, and you are not precise because you're not even getting consistently the same answer every single time. In science, we talk about precision in terms of the measurements or the devices that we use for measuring. So we actually, something like graduated cylinders, and you guys have a couple of different sizes of graduated cylinders that you use. We might, if I have a graduated cylinder that's only has a graduated mark every 10 milliliters, it is not as precise as one that has every single milliliter marked. And I think we know that. So it's just like if I step on a bathroom scale to weigh myself, because obviously I'm large, it works pretty good. But if I'm trying to find the mass of something like a pencil, my bathroom scale is not going to be very precise, right? Because it's just not sensitive enough. And that's also true in things in science. That's why when we measure liquids, we use graduated cylinders that have lots of graduations on them, and that's what these are. All the lines are considered graduations. I wouldn't tell you to find the volume of something, a small quantity of something, of a liquid, and I wouldn't tell you to do that in a beaker because it's not very precise. We wouldn't get very precise data, and so it wouldn't be very accurate either, because we wouldn't be able to be precise enough to be accurate. So that's kind of in terms of science. You know, when we talk about precision, that's what we're talking about. We also, the correct way to use these things is we can measure to the nearest, we can measure our degree of, or be sure of our degree of accuracy to the nearest measured number, and then we estimate one digit beyond that. So if I have a graduated cylinder that only is marked every 10 milliliters, the best I can do is, if I have a level of liquid that comes to right here, it's greater than 10 and it's less than 20, I can only estimate one digit beyond what's marked. So I might say this is somewhere between 10 and 20. I'm going to say it's 15 milliliters. And I can't say 15.5 or 15.25. I can only estimate that one digit beyond what I actually can measure with the device. That's the rule. If I'm measuring in, this is my ruler, I have every centimeter is marked on here, and technically it looks like on here that I also have millimeters marked. So I can measure it to the nearest, technically I can measure it to the nearest millimeter and then one digit beyond that. So I might say this is 13 point, and I can't really see this, 13.3, and then it's between the 3 and 4, so 13.35 centimeters. I can estimate that final digit. And the same thing with, we use electronic balances, so we don't really have to think a whole lot about that. But if you were using the pan balances like you used in middle school, same thing. You can estimate one digit beyond that. All right, so then how do I calculate the percent error that either of my measurements or limitations of my measuring device? And it's easy to do that. Calculating percent error. This is sort of reminds me of how you calculate your percent on a test, right? So there's a known and accepted value of our test, and then there's the number that you got right out of that whole number. So the accepted value is the correct value. So if it's a sample that I gave you, then it's my, let's see, that's really like, if it's what I gave you, then let's pretend that the accepted value, we're doing an experiment, and I gave you 20 grams of a substance. And let's say that based on the chemicals that we were reacting, our yield should have been 20 grams. But let's say you do the whole chemistry experiment, you weigh your mass of the product at the end, and you only got 15 grams. So my experimental, what I actually got was 15 grams. This is a G. It doesn't look like that because my writing's bad. 15 grams. Then what is my percent error? So what's the difference between that accepted value and the experimental value? Accepted value minus the experimental value. So I'm going to use actually this formula right here. My accepted value minus my experimental value. And it doesn't matter if you take experimental minus accepted. You're just finding the difference between those two. What does it mean when I put lines on my absolute value? So no matter what does that mean if it's an absolute value? What does that mean? It has to be positive. We can't have a negative number here. There's no negative percent error. It's always going to be positive. So 20 minus 15 is going to be 5 divided by my grams divided by my accepted value. That's 5 divided by, And then just, I want to multiply it by 100 to get it in percent. I should be able to do this in my head, but it's been a long day. All right, my percent error is 25%. That's terrible, right? Like, that's a lot. That would be really bad. Usually if we're within 5%, we're like, that's pretty good. Plus or minus 5% is pretty forgivable. 25% would be a really, really large error. Any questions on that? All right, so let's try one on your own. All right, so try that one on your own. Let's set it up. All right, let's set this one up really quickly. All right. So I want to take my accepted value minus my experiment. So I'm finding the difference between those two. What did we say? 12? All right, so if we calculate that all out, 12.5%.